Set theory. Set theory was discovered by Georg Cantor at the end of the 19th century when the foundations of mathematics were being examined. Set theory uses very simple concepts, collections of objects, that can be combined into complicated structures. A set is a simple, intuitively obvious base upon which a complicated superstructure can be built. An object is any distinguishable thing that you want to talk about, a physical thing, an abstraction, a process, whatever. A set is then a collection of zero or more objects, called elements of the set. Because each object is distinguishable, each element is distinct from each other element, other kinds of mathematical structures can deal with indistinct elements. The empty set is the set of no elements. It is intended that it is clear whether an object is in or not in a set, but it is difficult to formalize this intention. The first is the intersection of two sets, which is all elements common to both sets. Next is the union of two sets, which is all elements in either or both sets. The difference of one set minus another is all elements in the first set which are not in the second. Members in both sets are ignored. Members in the second set not in the first set are also ignored. Set difference is important because it introduces the notion of negation to set operations. One set is a subset of another if every element in the first set is also in the second. This is also said that the first set is contained in the second set. What is called vacuously true is all the elements of an empty set. Yes, we have no elements, are in every other set, so an empty set is contained in every other set. A proper subset is a subset which does not have all of the elements of the containing set. A proper subset is a little smaller than the set. An improper subset is a subset and can also be the entirety of the containing set. Consider two sets. If each set is a subset of the other, each has all the elements of the other, making them equal. All empty sets are contained in all other empty sets, so all empty sets are equal. Otherwise the sets are not equal. When an object is in a set, it is an element or element of the set. The cardinality of a set is the number of elements in the set. The empty set has no elements, its cardinality is 0. The cardinality of a non-empty set is greater than 0. Two sets have the same cardinality when we can find a one-to-one mapping between each element of one set and each element of the other. In particular, consider a set of the first positive integers such as 1, or 1 and 2, or 1, 2, and 3, and so on. We can set up a one-to-one mapping between a set of cardinality n and the set of the first n positive integers. This may sound a bit silly and obvious, but it becomes a powerful tool when dealing with infinite sets. The last operation is the power set. The power set of a set is the set of all of its subsets. Consider sets of 0, 1, 2, or 3 elements. The two-element set with elements P and Q had 4 subsets: the empty which is contained in all other sets, the subset of P alone, the subset of Q alone, and the improper subset which is the set itself. The power set is then the 4-element set with empty set, the set of P, the set of Q, and the original set. The power set of a 3-element set has 8 elements: the empty set, subsets taking 1 element at a time, subsets taking 2 elements at a time, and the original set of 3 elements. When the cardinality of a set is n, the power set will have 2 to the nth elements, hence the notation that power set of A is written 2 to the A. Each element of the original set will be a singleton subset in the power set, with a one-to-one mapping between the original set and a proper subset of the power set. The power set will have additional elements, for example at least an empty subset. This means the cardinality of the power set will always be larger than the cardinality of the original set. Thus, starting with the set, then its power set, the power set of the power set, the power set of the power set of the power set of the original. This creates a hierarchy of ever larger sets. Bertrand Russell used Cantor's set theory to define natural numbers, that is 0, 1, 2, 3, and so on, as particular kinds of sets. Based on the work of Gottlob Frege, they were trying to establish a rigorous foundation for what is a number. However, this depended on the notion that you could always decide whether an object was in a set or not. Russell came up with the paradox named after him that attacked set theory at this point. Consider the set of all sets that do not contain themselves. Does this set contain itself? If it does not, The set does not contain itself and so contains itself, but then if it does, it cannot. Russell's paradox comes from the apparent ease of defining a set but the actual inability to decide whether an object is a set. Set theory was discovered by Georg Cantor at the end of the 19th century when the foundations of mathematics were being examined. ZFC stands for Zermelo-Freenkel set theory with the axiom of choice. This is an axiomatizing of set theory that counters the paradox. If two sets have the same elements, they are equal, for any set X, and for another set Y, and for all objects Z which might be used as a set element. When each Z is in both X and T, the sets are equal. A set contains an element simpler than itself. Technically in Zermelo-Freenkel set theory are sets, sets of sets, and so on. Sets can express enough structure to represent numbers. The icons I have been using as set elements could be considered to be as representing distinct sets. Since a set's elements are sets, it makes sense to talk about a set intersecting its elements. This axiom only applies to non-empty sets, sets with at least one element. The empty set has no elements to be disjoint from. Two sets are disjoint if they do not share any common element. Since one of the sets is within the other, this means a set contains an element that is simpler than the set. For any non-empty set has an element which is disjoint from the containing set. When we intersect a set with each of its elements, they do not all have to be disjoint, but somewhere at least one element is simpler enough to be disjoint. We can specify a set as the subset of another set whose elements satisfy a predicate. Technically this is an axiom scheme, not an axiom. It is turned into an axiom by substituting the predicate symbol phi with a specific formula. The difference between an axiom and axiom scheme is due to the restricted kind of logic used with ZFC. For any set Z and predicate formula phi, construct a subset Y from Z from the elements of Z. Apply the predicate formula to decide if the element is in Y that satisfy the predicate formula. Y is the subset of Z that effaces. The set builder notation is used to specify the set Y identified in this axiom. It is read that Y equals the set of all X such that the condition after the colon is true. This condition is X is in Z and predicate formula is true. We can construct a larger set from two existing sets. Some of the axioms restrict of what a set can be but do not state whether such a set exists. This axiom is part of assuring we can construct whatever sets we need. For all sets X and Y, we can construct set Z such that Z contains X and Z contains Y. We can construct a union of smaller sets. The preceding pairing axiom allows us to construct the set F. This axiom allows us to disassemble F and reconstruct its contents as a union. For any set F whose elements are sets, there is a union set U. Such for each element X of each set E and F, that element is also in U. The binary union operator is used to represent the set U in the case F has exactly two elements. When a function is applied to a set, the image of the set is also a set. This is another axiom scheme which becomes an axiom on substituting the predicate symbol phi with a specific formula. A function in ZFC refers to a formula that is true for various values of X but only for one and only one unique value Y for each specific value of X. For example, X is equal to absolute value of Y is not a function since two different Y values. Solve the equation given X. However, absolute value of X is equal to Y as a function because different X can have the same Y. The image of a value X is the Y value. The image of a set is collectively all the images of the set elements. Then the function is applied to a set. The image is also a set. Natural numbers form a set. ZFC uses a different successor function than Russell proposed. The successor function does construct a sequence that is ZFC sets. The set starts with an empty set which represent the numbers 0, and adds each successor to 0, 1, 2, 3, and so on. The resulting set n is isomorphic to natural numbers. Note the cardinality of each element of n is equal to the number it represents. The power set of a set is defined. The power set operator was presented earlier. The subset relation is introduced to simplify writing the axiom. As before, the power set of a set is the set of all subsets. Given a set, enumerate all subsets of it. Note that one subset is always the empty set. The set receiving all these enumerations is the power set. And examples of the power sets of 0, 1, 2, and 3 element sets. The power set operator is the set Y specified in the axiom but without any extraneous elements. The last axiom, related to the axiom of choice, is that every non-empty set is well-ordered. This means there is a way of comparing the set elements so that there is always one element which compares to less than or equal to all the other elements. R is a predicate that takes two objects and returns whether the first is less than or equal than the second, for some notion of less than. An example of R for natural numbers is the usual numerical less than or equal. Another example of R on polygons would be comparing the number of vertices. Varying one of the Zeno's paradoxes, consider running to a donut. Since the donut will always be just out of reach, what is the minimum distance between Homer and the donut? According to this axiom, there is some notion of nearness. There is one position which the nearest. The naive notion will not work because Homer will advance, microscopically, past any position declared the minimum. The set of Homer must be well ordered according to the axiom, but the axiom does not tell what it is. Two quick theorems. The first is no set can contain itself. We construct a set that appears to contain itself, but then it no longer has a disjoint element, leading to a contradiction. Because no set can contain itself, Russell's paradox is apparently defeated. Overcoming this paradox was motivation for ZFC, apparently defeated because it is possible to create names for sets and thus indirectly include a set within itself. The second theorem is the axiom, Ney theorem, of choice. Like well-ordered axiom, it states existence of structural information without specifying how to get it. The well-ordering is equivalent to choice. Either can be taken as the axiom and the other a theorem proved from the axiom. We can construct numbers out of sets. Natural numbers can be defined in other ways which can lead to differences in provability. I use these constructions to show how complicated objects can be built from simple components which are just sets. First, consider the Cartesian product which produces a set of ordered pairs. An ordered pair is different than a set of two elements because the order of the elements is preserved. Who is on first matters. Also, an ordered pair has two distinct elements even if they are identical. The construction is by Kuratowski with the ordered pair AB as a set is the set of two elements, a set of just A, and a set of A and B. It is easy to extract the individual set elements, taking care to check the cardinality for a collapsed pair. A Cartesian product of two sets is the set of all ordered pairs with the first pair component from the first set and the second from the second set. The first set of numbers are the natural numbers, 0, 1, 2, 3, and so on without limit, and this is the set n from the axiom of infinity. We define addition as the repeated application of the successor. Addition is closed on natural numbers, which means adding any two natural numbers is another natural number. It is closed because it only uses 0 and its successors. Closure means that applying an operator to elements of a set will be another element of the set. Closure will motivate for extending sets of number. The inverse of addition, called subtraction, x minus y, is the number z such that y plus z equals x. However, subtraction is not closed. Specifically, 0 minus 1 is not a natural number, it is undefined. We can close subtraction by adding extra numbers for the uncompleted subtraction. This new set is called integers. An integer is an ordered pair of natural numbers. Equality of integers is not just equality of components. Different order pairs can be equal integers. Every integer is equal to an ordered pair in which the first or second component is 0, or both are 0. The first case are called positive integers equal to the first component, the second case are called negative integers equal to minus the second component, and the last is 0. Addition and subtraction of integers are done as addition of the appropriate natural number component. Addition of naturals is closed, so addition and subtraction of integers is closed. Now we define the operation multiplication as repeated addition. Since multiplication is defined only in terms of addition and subtraction, it is closed on integers. The product of two integers is always an integer. We can also define the inverse called division. X divided y is the integer z such that z times y is x. However, 1 divided by anything but 1 is not any integer z. Division is not closed for integers. An additional complication is that 0 times any number is always 0. Because of this, any attempt to define an inverse, a division by 0, results in something that breaks various properties of multiplication and division. For the moment, closing division by 0 will be skipped. Only closure by a non-zeros will be pursued for now. We can close division by any non-zero integer with a new set of numbers to represent uncompleted division, called rational numbers. Multiplication and division of rational numbers is done as multiplication of integers, which is closed. Multiplication of rationals and division by non-zero rationals is closed. We define a rational sequence as function from natural numbers to rational numbers. How long is it? It is long enough. The sequence is called a Cauchy sequence if the elements of the sequence get closer and closer the further out in the sequence. When these sequence elements comes closer and closer to the same number, the sequence converges to that number, also called its limit. A simple Cauchy sequence is 1, 1, 1, 1, 1, and so on, because for any tolerance starting with the 0th element, the distance between 1 and 1 is 0 and less than any tolerance. The sequence converges to a 1. Another Cauchy sequence is 1, 1/2, 1/4, 1/8, and so on, which converges to 0. We have various ways to construct a sequence of rational numbers that converges to the square root of 2, but the square root of 2 is not a rational number. Not all rational Cauchy sequences converge to a rational number. Now consider the sequence of Fibonacci numbers divided by the next smaller Fibonacci number, or 1/1, 2/1, 3/2, 5/3, 8/5, and so on. This is also a Cauchy sequence, but it does not converge to any rational number. While the sequence might appear to converge to a rational number, it will eventually veer away from each rational number. Because not all Cauchy sequences of rational numbers converge to a rational numbers are called incomplete. We can create a complete set of numbers by including rational numbers and the limits of all rational Cauchy sequences. The set is called real numbers. Every Cauchy sequence of real numbers converges to a real number. Completeness can be thought of as a kind of closure of Cauchy sequences. Real numbers are a complete set of numbers, which means any sequence of real numbers which converges to a real number. There are no gaps in real numbers. Real numbers inherit the previous operations, called the rational operations, of addition, subtraction, multiplication, and division. Now we define the operation of power or exponentiation as repeated multiplication. Powers are defined asymmetrically. The first operand, the base, is a real number, and the second, the power or exponent, will be restricted to natural numbers for now. While it was not proved, multiplication and addition commute, that is, the operands can switch order without changing the value. Exponentiation does not commute. Since exponentiation is defined only in terms of multiplication and addition, it is closed on real numbers. The power of real number to a natural is always a real number. We can also define an inverse called the root. The nth root of x is the real number z such that z to the power of n is x. However, when you multiply a real number by itself, the multiplication produces a positive real number regardless of whether the original number was positive or negative. The second power, or square, of any real number is non-negative. The second root, or square root, of a negative number is not a real number. Similar to the division by 0 problem, the 0th root of a number cannot be easily defined without losing a more useful property elsewhere. The preceding defines 0 to the 0 power as 1, but this is another expression that is problematic, and often it is left undefined. We can close the root operation by adding extra numbers to make the complex numbers. We only need one extra number, the imaginary unit, which is the square root of -1, on which to build all roots of all negative real numbers. Exponentiation in complex numbers requires the use of Euler's 27's formula. The power operator can be extended so that any complex number can be raised to any other complex number except 0. The inverse of exponentiation can also be defined as a logarithm. Logarithms are closed, except again for 0, for complex numbers. While closure of division by 0 can be done, naively doing so breaks the system. The inverse of 0 cannot be a real number or a complex number. When done with care, a new kind of number can be added to complex numbers, but in doing so many useful properties are lost. For example, when working with complex-valued function, it can be convenient to extend complex numbers to what is called the Riemann sphere, where division by 0 is allowed, but subtraction, multiplication, and division are no longer closed, and some reciprocals are undefined. By the axiom of infinity, the natural numbers are an infinite set. Like finite sets, infinite sets also have a cardinality, the size so to speak, but the cardinality, unlike finite sets, are not natural numbers. They will be named later. Two sets have the same cardinality if there is a one-to-one mapping between the sets. If we can find a one-to-one mapping between natural numbers and some subset, or the entirety, of another set, the other set is also infinite. A set which is not infinite is finite. A finite set has a one-to-one mapping between the set elements and the first are consecutive natural numbers. The cardinality of such a finite set is R. When a set has one-to-one mapping to a subset of naturals, it is called countable or denumerable. All finite sets are countable. The set of even numbers also has a one-to-one map to natural numbers. Double natural numbers are even numbers, and halved even numbers are natural numbers. Even numbers are infinite and denumerable, even though the even numbers skip every other natural. By hopscotching between negative and positive ends, the set of integers also has a one-to-one map to natural numbers. Integers numbers are infinite and denumerable, like even numbers. While even numbers skip naturals whilst still denumerable, integers have additional elements and still denumerable. It should make sense that integers are countable because, like naturals, no integer can appear between two consecutive integers. I might say integers cannot be compressed. However, between any two rational numbers is another rational number, and between those another. As Zeno's revenge, it seems we cannot count the rational numbers between 0 and 1 before counting those between 0 and 1/2, between 0 and 1/4, 0 and 1/8, and so on to ever smaller first steps we cannot make. However, each rational numbers is comprised of an integer and a non-zero integer, so while rational numbers are in a sense compressible, their numerators and denominators are not. We can list rational numbers on a quarter plane, using on positive naturals as coordinates, place numerators on the vertical axis and denominators horizontally, then traverse the plane diagonally from the origin, from the denominator line up and to the right to the numerator on the right. At each point in this lattice, enumerate the fraction and its additive inverse when the numerator and denominator have no common factor. Add a special case for 0 at the beginning. Because all possible positive numerators and denominators are listed, and diagonal sweeps will eventually pass through every combination, all rational numbers will be eventually reached and enumerated. Rational numbers are countable and infinite. Rather than cope with the entirety of real numbers with an infinite distance to the positive and an infinite distance to the negative, it would be convenient to work with a smaller set, say just those real numbers greater than 0, but less than 1. Recall two sets have the same cardinality if they have a one-to-one mapping. By restricting the function to the interval 0 to 1, every fraction maps onto a unique real number covering the entire range. As it approaches 0, it decreases without bound, and increases without bound at 1. Inverting this middle band produces the function that does the opposite, mapping each real number to the range 0 to 1. Since real numbers and the interval have a one-to-one mapping, they have the same cardinality. The interval 0 to 1 can stand for the entire set of real numbers. What is the cardinality of real numbers compared to natural numbers? This is answered in Cantor's diagonal proof. Assume they have the same cardinality, then we can make a list of all the fractions. The fraction's position in the list is the natural number it is mapped to. Now construct a fraction. Its first digit is the first digit of the first row plus 1. The second digit is the second digit of the second row plus 1. The third digit of the third row plus 1. This continues down the entire infinite list, constructing an infinitely long fraction. Note this new fraction cannot equal the first line because one digit has been altered, nor the second line because the second digit has been altered, and this continues down the entire list and the new fraction is nowhere on the list. That means the assumption is wrong and real numbers are not countable. This is Gay-or-Cantor's famous diagonal proof, so called by constructing a counterexample from the diagonal of the list. We also see real numbers have at least one more element than naturals, and so they have a larger cardinality. Real numbers are an uncountable infinite set, also called a non-denumerable set. The names of cardinalities of sets are called cardinal numbers. Natural numbers are included in cardinal numbers, and name the cardinalities of all finite sets. Additional cardinal numbers, called transfinite cardinals, name cardinalities of infinite sets. Cantor named the cardinality of natural numbers as Aleph null. Aleph null or Aleph 0 is the first of an infinite hierarchy transfinite cardinals. The power set of an Aleph null size set is a larger set whose cardinality is called Aleph 1. The power set of an Aleph 1 size set is an Aleph 2 size set, and this can be continued without limit. The cardinality of real numbers is called C for continuum. Cantor tried but failed to prove that C equals Aleph 1. Since him, others have shown that this cannot be proven. You can take as an axiom that C is strictly less than Aleph 1 or that C is equal to Aleph 1 and get a consistent set theory in either case. A subset of decimal fractions have two equal representations, those ending in all 9 and those ending in all zeros. As numbers these are equal, but as strings they are different. I see this as adding a fuzziness to real numbers that leads to this improbability. Complex numbers are represented as the Cartesian product of set of real numbers with itself. Consider an ordered pair of real numbers. Represent them as two decimal fractions. Treating the decimal representations as strings, construct a new fraction by interleaving the two strings of digits. We can reverse this and turn one fraction into two real numbers. This is a one-to-one mapping between a single real number and the Cartesian product, so they have the same cardinality, and real numbers and complex numbers have the same cardinality. We can apply the Cartesian product to real numbers any finite number of times and we still have a set of cardinality C. This means any finite dimensional real space or complex space has the same cardinality as the real line. Natural numbers are used to both count how many, such as 1 apple, 2 oranges, 5 kumquats, but also to order things in a list, such as the first apple, the second and third oranges, and the fourth, fifth, sixth, and seventh kumquat. The first use, counting how many, are cardinal numbers. Cardinals start with natural numbers, continue with Aleph cardinals, and continue beyond. Just as cardinals can be transfinite, so too can be ordinals. The successor function orders naturals in any set mapped into naturals. The ordinals of a finite set are natural numbers. The limit as the ordinals increase without bound is omega, the first transfinite ordinal. The subscript of the Aleph cardinals are ordinals, so we have Aleph null, Aleph 1, Aleph 2, and so on to Aleph sub omega, Aleph sub omega squared, and never-ending hierarchy of larger and larger infinite sets. What most people think of as infinity, the size of natural numbers, really is a tiny, tiny beginning of an infinite hierarchy of infinite sets. Luckily for practical purposes we only need to first few levels, Aleph null for countable sets, Aleph 1 or C for real number, and Aleph 2 for sets of functions. A countable set such as rational numbers has gaps around its elements. A converging sequence might lead to a gap rather than an element of the set. Such a set is called discrete in reference to the gaps. A non-countable set like the real numbers has no gaps around its elements. Every convergent sequence of real numbers leads to some real number. These sets are continuous, as in the continuation all the way to the element. Discrete, including finite, and continuous maths have similarities, but the continuities and discontinuities have to be dealt with. An important concept is that infinity is not a simple concept. Even ignoring the hierarchy of infinities, we have profound differences between the smallest infinities that must be accounted for.